I need to stay here.
You can stay here. Good morning.
Morning.
Good. Dr. Likrens, you are welcome again.
Thank you.
Yeah, I think we can start while others join. I think many of them are already joining. But I think we can start while they join. So I welcome all of us again to today's session. This is day 3 of the Summer School on Space Technology and Applications 2026. And today we are going to take on an important topic, which is on space exploration. As usual, there will be 2 segments of the presentation. But for now, the presentation will be led by Sir Franklin Onna, who was a research scientist with National Space Research and Development Agency in Nigeria, but currently a lecturer at the University of Nigeria, Nsukka. He's a specialist in space science and space research, and we will listen to him for this first segment of lecture. So, Frank.
Yes.
Over to you.
Good day, everyone over there that are part and parcel of this school and program. It is my pleasure to be here and to be the one to lead today's lecture on space exploration and space robotics. So you're all welcome. I hope you've been having a good program. Yes, I would like to start by outlining the areas that I will touch on in the area of space exploration and space robotics. Yeah. So I'll first of all like to start with an introduction that makes us know the context in which the whole space exploration quest of humanity began, how it was related to the older interest in space, which was through astronomy. Then we will now delve more into what space exploration is all about and what we have achieved so far. And then we can also look at space robotics before we now go to the concluding part. So in terms of introduction, I would like to remind us that this is a journey that has been long, but the longer part of it in terms of humanity's interests in the universe and in the celestial bodies in space, one would like to refer to as the astronomy part, which is something that is done from the platform of the Earth, the home planet, yeah. That has been there for thousands of years of history. The history of astronomy has spanned thousands of years. But with the progress of science and technology, we now reach the point where we could now actually take some sojourn into space with spacecraft and with manned missions to be able to go and then study, explore, interact with some of the celestial bodies we have been observing and studying by their radiation through astronomy. And that was, so the whole idea of space exploration started in the middle part of last century, around the late 1950s and early 1960s. Started by Russia with the launch of the first artificial satellite Sputnik in 1957. Then other missions followed. which led also up to a sort of space race between the two powers then. And we now had the Apollo mission to the moon. That was a manned mission. Before that, we had launch of satellites and also launch of men into orbit by the Soviet Union and the United States. So those were early beginnings of the space exploration quest of mankind. Today, we're in the year 2025, and if you project from that early beginning, we are now like 60 years, 60 years of the space activity. So we now have a situation where between then and now, a lot has been achieved because it kept on developing and progressing. So the aims of this whole activity of exploring space, a lot of it has to do with scientific goals, scientific research, also technological advancement, then also the quest for resources and habitation. That is in terms of resources that could come from space and also habitations, colonizing and living in space. Those are the driving goals. So if we are now investigating the space, when it comes to the space exploration, there are really two directions. One is unmanned spacecraft, robotic spacecraft, with which we now try to explore the heavenly bodies. Then the second option is human or manned space flight. That is when human crews now go in spacecraft to space. These are the two major forms in which the space exploration takes, and each one comes with its own merits and demerits, and we will see the evolution in which direction the space exploration effort is now proceeding and where we are today. So if we really take a historical view of the space effort, between the launching of probes to the manned mission to the moon, other missions to other planetary bodies in the solar system continued. We had missions to Venus, Venera. We had missions to Mercury. We had missions to the outer planets, Mars, Jupiter, Saturn. In fact, as things stand now, most of the solar system planets and many of the moons have been explored or visited by unmanned spacecrafts. And as things stand now, Voyager 1 and Voyager 2 are two spacecrafts that were launched to cross to the outer part of the solar system and are already on the verge of leaving the boundaries as defined by the heliopause, crossing the boundaries of the solar system. Yes, although they are still within the Oort cloud, but they're already on their way out to become interstellar spacecraft or probes. So one could think of them as like the early or initial beginnings of the possibility of interstellar travel. Because so far we have been restricted all this while to explorations within our own solar system. That is the sun and the planets around it, of which our Earth belongs. But then we know from the study of astronomy that the universe is a very big place. Even the billions of galaxies, and even the galaxy that we belong to, the Milky Way, hosts billions of stars. So the discoveries of recent day astronomy is that many of these stars host their own planetary system, groups of planets. And therefore, the vista of opportunity for the study of celestial bodies has extremely widened with the discovery of extrasolar planets in all these other stellar systems. So we now have a situation where the possibilities have gotten wider, but we can see already by looking at the immensity of the universe and the planets that are available to us. And when we compare it to where we currently are, we can conclude that we're still at our baby steps in terms of the exploration of the universe. Currently, we're basically restricted for now in terms of manned and unmanned space exploration to our own sun and the planets around it. But we can see that there are so many other possibilities. But also with these other possibilities, the constraints are also what? Much more. The constraints and challenges are also much more, because you're now going to deal with instances that are much more than what we currently have within the solar system. Of course, it's clear that the distances separating the stars are in light years, but within the solar system, we're just talking about astronomical units. Those are two different orders of magnitude. Yeah. So that is it in terms of like the motivations and some of the history of the exploration of space. Yes. Of course, as is usual with every beginning, during the onset of the space age and space exploration in the 50s and 60s, there was also a lot of optimism and a lot of hope and expectation, and one could also say hype in terms of over expectation about successes in the space arena. But of course, the reality of the explorations has brought us to the fact of certain limitations. And we find that since the Apollo lunar landing, that has been the only manned mission that we've had to another body outside the Earth. And some people were already surprised. They thought that by now that there will be regular manned missions to many of the other planets. In this lecture, we will try to address some of those challenges and limitations that prevent those over-optimistic expectations that prevented them from being realized, and where we are, what directions the space exploration efforts might likely take as we draw into the future. So we now have, that is the angle of space exploration. So we've had a manned mission to the moon in the late 60s and 70s. And then we've had several unmanned or robotic space probes to most of the other bodies of the solar system. That is the current state of the art where we are. People can easily read up details about each specific mission, each particular planet. And a lot has been learned about the universe, starting with our solar system. Why I say the universe is also because the details of the information we have learned about the members of our own solar system, they don't just provide us information about ourselves, our own solar system. They also become the yardstick and the reference with which we use to what? In our investigation of other planetary systems, other exoplanets, other parts of the galaxy. We use the detailed information we have gathered about our own solar system as a base mark, as a reference in now, relating to and talking about the other extrasolar planetary systems that we have less information about because of their distance and the fact that we can only access them through radiation. Now, I'd like to mention one particularly significant thing, which is the relationship between space exploration as it is done and the traditional and modern astronomy. We can already begin by distinguishing the two. In astronomy, we're far from the celestial bodies, and we're trying to study them using the light and other radiations and other sources of channels of information coming from those celestial bodies. So we don't have direct contact. So we are also affected by the limitations of distance and the limitations of radiation, the speed of light, the nature of light. But through astronomy, we do learn a lot of information about those remote celestial objects. Then in the area of space exploration, we're now using technological tools that can travel, that can go and have direct measurement and exploration of those celestial bodies. These two areas work hand in hand. They are complementary. Because even before we go to travel to the moon or Mars, it is the information already provided by astronomy that forms the base of the planning and the calculation. Otherwise, the effort may not really be so much for it. It's like a flying blind. You're going somewhere you don't even know anything about. But in this case, astronomy has already provided the foundation. Then we now plan a space mission with the astronomical information as a guide to where we are going. Then secondly, that is conversely, when we now send a probe to an outer planet, for instance, Jupiter, we now get more detailed information about that planet and the moons around it, much more than it will be possible to get using only telescopic observations through astronomy. So astronomy already provided the base. Then the space mission now went and filled in further details because there's a big difference in what you can find out and measure when you're already down there, when you're already close. The resolution of the information you can find out is much more when you are very close to the object. But when you are distant, you have less information, okay? Or you have an overview, but you have less information. So the two are meant to be working hand in hand together. And only when we have a high enough technological capability can we undertake that of space exploration. But astronomy, one could say, comes easier because even with your naked eye, without any instrument, you already have started doing astronomy. But then as instrument more, then you do better astronomy. Yeah. The only part of space exploration that it is possible to do while on Earth will be something like the study of meteorites, which are space objects that have fallen to the Earth. So it's like space came to you, to the Earth. So you can now study those objects without necessarily having to go there because the objects actually fell to Earth. Okay. So that is it in terms of the relationship between astronomy and space exploration, which I said that they are complementary and are meant to work hand in hand together. Yeah. Okay. So before I come to the constraints and limits to our space exploration efforts, especially manned space exploration, I'd like to talk about space robotics. This area involves the designing of unmanned, that is unmanned in this case is that there's no human crew. So this spacecraft or the launch vehicles are kind of autonomous. They are remotely controlled, computer-controlled devices. One of their characteristics is because they are machines, that they are, artificial objects. They don't have humans. Their window the window of the conditions they can withstand are broader. You can find that they can withstand extreme conditions that are found in space. So much more extreme than the ones that humans can withstand. So we now find out that is why they have been able to explore many of those places that humans have not been able to go because they can be built to withstand extreme conditions in space. Yes. So we can think of them as like extensions of the human quests. Where we have limitation, then let our machines and our spacecraft help us to go where we may not currently be able to go. So that is what we find in the space robotics. So these spacecraft help to mitigate the risks to humans that would have when they are directly in space. The space robots and other autonomous vehicles and instruments that we can send now help to mitigate the risks of space human bodies. Then the types of these space robotic devices, we have those that are orbiters, those that are sent to be able to move in orbit around a planetary body or moon. They are called orbiters. Then we also have those ones that are designed to go and land in the planets. They are called landers. Then we have those that autonomous vehicles that can navigate in the surface of a planet. Those ones are called planetary rovers. These are all different forms that they can take. Then we also have some humanoid robots that can also have the form and behavior of humans because they are designed that way. That can also help us do one thing or the other in space. So these are all the forms they can take. So they are able to endure vacuum. Of course, we are aware that a human being cannot stay in the vacuum of space, except if he's under a high pressure spacesuit. But these devices can be designed to be in the vacuum of space, and yet they will not be destroyed by that condition. Then also the incidence of high radiation, cosmic radiation that is in space. We're going to talk about that because it's also a limitation of the ability of humans to, be sent to many places in space. There are certain limitations that come due to the exposure to the high intensity of cosmic rays in space. So you now find high pressure, high gravity or low gravity as the case may be, then fluctuations of temperature from high extremes to low extremes. Robotic craft is better able to be designed to, at lower cost, to be able to withstand these conditions than manned missions. Yeah. So when these robotic spacecraft are sent to space, there are two different methods of their link to humans on Earth, because the humans, the engineers and the scientists who build them and who design them and who send them still have to have a link to it to be able to, otherwise they are on their own and there won't be any link to human beings again. So there must still be a link. So what are those kinds of links? The links are in two ways. The forward link is trying to control them and tell them what to do. Okay, that's the forward link. Then the back link is receiving information back from them. Okay, either feedback information or data information, because they're going there to take measurements, measure things, get information, take pictures. So all the data that are gotten by them must be what? Telemetered back to us. So you now find that the system is designed in such a way that there will be a way that the spacecraft can send information back to the base, to the humans who are the designers and the launchers who control it. So there are two methods in this telemetry. One is real-time, that's real-time teleoperation, which means that the spacecraft is being controlled in real time or near real time as it is operating, meaning you can tell it, do this. Oh, so this is what you're seeing, do this, or do this other one, and do that other one. So you're like communicating with it real time. But then there's a second method because there's a limitation to real time or near real time telemetry. That can only be done for near space mission. There's something called the speed of light. It is very, very big. And the astronomical distances are also big. So when the astronomical distance becomes very big, the time of flight of light signals or radio signals will correspondingly become more. So a trip to Mars by light is a few light hours. So it takes like some hours to be able to send a message to Mars and then another few hours to get the message back. Compare that to the moon, where it takes only 1 second of signal time to be able to send a message to the moon. So if you are linked with a spacecraft on the moon, then you could do almost real-time communication with it. As a sensing, you're telling it what to do, and there will be a feedback. But that's because of 1 second delay. But when you have hours of delay, that's no longer possible. Do you see? So we can now not have near real-time telemetry. So we now have a system where the spacecraft is designed to be more autonomous for those longer missions, longer distance missions. So you now have where the spacecraft is autonomous and it's driven more by AI, artificial intelligence. So it's programmed in such a way that whatever it is meant to see there, it should be able to react to it without connection with ground station. Then whatever reaction is doing, the data is getting, it should be recording it so that later on, when there's a telemetry connection, then all that information it has gotten will be what? Sent back to us. Because we're the final receiver. We're the one going to process this information, learn from what it has experienced there, measured there. We're the one, remember, who designed the mission. So we are the final what? The final consumer of that information. So the spacecraft is just, I don't know what. I touch something. So I can still be talking. Yeah. So we are the final consumers. So the information finally has to reach us. Oh, that's great. Cool. So that's what happens in space space robotics. Yeah, space robotics. So I should continue. Okay, fine. So I think we can dwell now more on some of those technicalities, some of those constraints that were limits or pose a challenge to easy and quicker exploration of space and to manned missions, especially to manned missions. Yes, and what directions the future of space technology seems to be evolving towards to be able to mitigate some of these limits, some of these limits. Yeah. So I'll try to itemize them. The screen. Okay. That's the beginning, actually. Yeah, you can leave it here. Yeah. Okay. So, ladies and gentlemen, yes, we're trying to talk about the limits and challenges that constrain us in terms of manned missions and more quicker exploration of the outer planets and the other parts of the system. Yes. Yes, initially we mentioned the challenge of cosmic radiation. Yes, cosmic radiation. So cosmic rays from astronomy, astronomers study cosmic rays. They are one of the channels of astronomical information. These are the highest energy subatomic particles, fluxes of them, that come from all directions in space and impinge on the Earth and on all other celestial bodies. They don't have particular directions because they are randomized in space. Of course, they have sources, astronomical sources or what have you, but during their motion in space, they are randomized by magnetic and electric fields. So we no longer, they come omnidirectionally on Earth. They also impinge on all the other celestial bodies within the solar system, within the galaxy, even beyond the galaxy. There are characteristics that they are there in a cosmic space. So, they are very high energy particles, and high energy particles are of the ionizing kind. Ionizing means that they have deleterious, injurious effects to living systems. Even non-living systems are affected by ionizing radiation, which affect the structure of solids and other technological objects because of the energy and the ionization that they deposit in the materials. So, but they particularly affect living systems because living systems are more delicate systems. They are made up of biomolecules, and these biomolecules have certain delicate behaviors. So they are affected. Those ionizations lead to breaks in the molecules and lead to ionizations, which is what they call mutations. And these mutations can lead to what? Cancerous and malignant tumors. So yes, on Earth, cancers are due to certain chemicals and also certain radiations. Of course, nuclear radiations are part of it. Cosmic radiations are also part of it. But the interesting thing is that with respect to cosmic radiations, we find out that there's a natural mechanism that protects the inhabitants of the Earth, humans and other living things, from the high intensity of cosmic radiation that is available in space. And that is no other than, most importantly, our atmosphere. That is the gas of our atmosphere. Yes, the protective layer around the Earth are in many forms. There's the magnetosphere. There is the sheer atmospheric mass gases of the atmosphere. Then, of course, there's the ozone layer. They all play their different roles, because what the ozone layer protects us from, the high energy UV of the sun, is quite different from what the magnetosphere protects us from, which is the solar highly energetic charged particles, which it deflects towards the poles that forms the auroras. Then the gases of the atmosphere themselves protect us from high energy cosmic radiations. They all play their different roles. So with all the studies about ionizing radiation, we're beginning to learn more and more about this protective effect of the atmosphere, what it has been doing in protecting humans. So the exposure, those who study radiation measure it in Soviet exposure and doses of radiation. And they know these doses, that the level of doses that are safe and the level of doses that are dangerous. Yeah. So studies show that our atmosphere protects us practically from almost 99% of the exposure we would have had in space. So that's quite a lot of protection. So you now find out that once we leave the atmospheric shield, okay, then we now have that problem of, at least living things, now have that bigger problem of how to protect yourself from that intense exposure, which happens whether you're in a spacecraft or outside a spacecraft is the same, because the penetration ability of the cosmic rays goes beyond the thicknesses of the walls of spacecrafts. Before you talk about an adequate protection, the level of thickness of the material of the spacecraft will have to be thick to almost be uneconomic. So that is the current challenge. So when you're in orbit, there's a level of exposure. That's the orbit around the Earth. It's not as intense as when you're in out to outer space, meaning beyond the vicinity of the Earth. So there's a kind of level of exposure you get when you're in orbit. There's another level you get when you're out in space, in interplanetary space. Then there's another level of exposure you get when you are at the surface of a planet that doesn't have an atmosphere. Think of the moon. Think of Mars, for instance. Mars has an atmosphere, but it's not as dense as that. It's a very thin atmosphere. So it's near to what you could say a vacuum is. So what it means is that this is one of the challenges to manned missions, okay? It's not like, of course, they went to the moon, but remember that they didn't stay, the stay on the moon was short, because also the exposure has to do with the length of time you're exposed to the radiation. So it's not like humans can't step out into space. They can, of course, they have already done that, but it limits how long they can stay if they want to remain healthy, unless they have to go through bigger mechanisms to be able to protect them, which makes the mission and the craft to be much more expensive or inconvenient. So that is the problem of the limitation of radiation. Of course, this is still work in progress. Research is still on to find ways to mitigate radiation problem, but currently it is still a challenge. So that's one. Then you now find that we have another issue. Another issue is energy. Because all this traveling to space, don't forget, they come at a cost, an energy cost. It takes quite a lot of energy to do launches, to launch spacecraft, because you have to burn fuel in rockets, build the rockets and launch and burn fuel in them. And anyone you're propelling to another planet, you either use some gravity assist or you must use propulsion. That means you're burning fuel. And all that fuel have to be carried in the spacecraft, okay? So it also places a limit to the size of the crew, the size of the payload, the amount of fuel you have to carry places a limit on the payload. So now, and currently, most of the energy proportion for space comes from what? Burning fuel. That's chemical energy, chemical fuels, which means fossil fuel, basically. Most of the energy is derived from fossil fuels by carrying both the oxidant and the fuel. You burn them in the rocket or spacecraft and generate your thrust and then control the thrust. So chemical energy has its own pros, but remember the rocket equation also places some limits because of the mass, the sheer mass you have to carry and the energy density. That's also why people are also exploring the possibility of using nuclear power in space to propel crafts. So there are systems that are working on using nuclear power for space propulsion, nuclear thermal propulsion systems, and other novel systems that may not yet be practical, but the hope is that they will replace and overcome the limitations of fossil fuel so that more payload could be carried that could stay longer without its fuel finishing, because these are the problems. Once the fuel finishes, you can't move any longer. You cannot navigate in space. Or possibly any other new sources of energy that might even be more convenient than nuclear, because nuclear also has its own dangers and limitations. Yes, there is the possibility of using solar power. That's like solar panels on spacecraft. But if you realize the energy density problem of solar energy, and the high energies that are needed by spacecraft for propulsion and other tasks, then you know that solar energy may not be a major energy component. Okay, it can help, like satellites. A lot of satellites use solar panels, but don't forget that even the satellites that use solar panels for their electricity have to have fuel for their propulsion to do attitude control. That is why the lifespan of a satellite is restricted to maybe 10 years or 15 years. When the fuel finishes, then it has to be deorbited, because you don't use the energy from solar panels to be able to control the attitude and orbit of a satellite. So there are energy challenges too. So it is some of those energy challenges that have also been barriers. And if on Earth, we're also talking about the non-renewability of fossil fuels, which means that there's even an energy problem on Earth, because if we have based civilization on non-renewable energy, we're saying what will now happen when this is going down because it's being consumed faster than it's being generated? And what will now happen? What will the whole civilization, and of course the space exploration that depends on the civilization, when we are lacking energy? We're already at the phase where energy is no longer abundant and people are hustling for it globally. So we're saying there's an energy problem on Earth, which also translates that there will be an energy problem for space missions and space exploration. So the hope is that this energy problem will be addressed. There will be a viable solution to it. Otherwise, it will also affect all things that civilization do, whether it is data centers and AI, or whether it is space exploration. It will be affected by energy constraints. So you now have space. So that's one of those limitations. Then there is another particular one that is pertinent to mention, which is we have a problem of human. What is a human life support system? Let me put it that way: human life support system. For you to have a manned mission where there's human crews that will leave the Earth and stay long away from the Earth, then you need adequate provision for the human life support system. I mean, the human beings have to eat food, have to drink water, have to breathe air, and any other thing that makes their condition okay, including control of temperature, pressure, adequate gravity. So you see, their needs are more. The needs of humans in space are defined. So when we now have a problem of this life support system has to be made available, Okay? So if you don't have a system that regenerates the life support system while you're in space, then you're going to be dependent on continuous supply from the Earth. And remember, as the missions go further away from the Earth, the logistics of resupply will become more problematic. Okay? So if you're going to be on Mars, for instance, missions to Mars take like months to a year to be carried out. I just told you that speed of light, it takes light a few hours, but that's light. If you're not going to travel at the speed of spacecraft, it will take you months to a year to get to Mars. So you see the logistics of resupplying a craft that during the resupply mission, it will take you many months to 1 year. So that's the real logistics problem. So the research has been going in the direction of trying to see whether we can have a regenerative sustainable life support system. This goal is motivated by considering the Earth as an ecosystem. The Earth is a life support system, and it keeps providing the food, water, and air continuously because it's regenerating it. That's the oxygen we breathe out, for instance. We breathe in oxygen, breathe out carbon dioxide, and the plants change the carbon dioxide, use the carbon dioxide, and bring out oxygen. You see the balance there? So there's a regeneration. So you now find out we are now trying to mimic that system and find whether we can evolve a system that a human life support system that can be regenerating both air, water, and food, meaning maybe growing food in space, for instance. Research is in that direction to be able to see whether you can grow food in space so that you don't need to be resupplying from the Earth. Because resupplying from the Earth places a lot of constraints on you. If you're talking about going to another planet, Mars, for instance, and having a habitation there, then if you're not going to depend on resupplying with its problems, then you have to have a regenerative autonomous system. So now, this particular issue about trying to have a life support system that is regenerative and sustainable, there was a test case of it on Earth called Biosphere 2. Biosphere 2. The biosphere is the name for the Earth's ecosystem as a regenerative system. So Biosphere 2 was an experiment on Earth to try to see whether we could design such a small-scale life support system that will be sealed from the normal biosphere, just maybe a containerized system where you have plants, you have humans, see whether you could have it working out. And a lot of lessons were learned from that experiment. It did not really go as it was hoped. But even from the challenges and failures of the biosphere experiment, lessons were learned about life support systems. Maybe we were initially over-optimistic about how it works. And from the lessons there, the hope is that maybe we can do it better and we could find a system that can be of use and application in space. Yeah. So that is the issue about Biosphere 2 and evolving a next generation human life support system that could be used in space. So I've mentioned the challenge of cosmic ray and of course gravity too, because remember that humans evolved and that is adapted to the conditions on Earth with 1G as their normal gravity. So our bone structure and other physiological conditions are not really adapted to zero gravity, lower gravity, or hypergravity. And these are things that we will be exposed to in space. So the astronauts get exposed, they suffer some physiological problems because of that. There is bone loss and bone brittleness. These are things that have been documented. So you now find out that research is also working on possibility of providing artificial gravities or finding ways to mitigate those physiological bone effects due to lack of the right Earth gravity by astronauts and other space explorers. So it is some of these limitations that have bedeviled the quick rollout of manned space missions for the past 60 years. Because some younger people who were not even there in the 60s when the moon mission was done, some of them are wondering, why are we not regularly on the moon? Men are not regular. After having gone to the moon 50 years ago, why is this such a problem now that there's no regular trips to the moon? I mean, that was the expectation, but that's not the case, okay? So you now find out that there is still the goal of return to the moon, but the direction of the space exploration effort shifted a little towards what I would say is easier and more efficient and less limited by these constraints. And that is what? Robotic space exploration, space robotics. So the space exploration shifted more towards space robotics than manned space missions. And the reasons are because of these constraints that bedevil human space exploration more. So you now find out that when missions are launched, robotic missions are launched, we then need not to worry about too much about cosmic radiation, at least not to the same level we worry about it for humans. Then the problem of human life support system will be knocked off. You get that's the problem of human life support system, because robots and computers don't require what? Human life support. All they need is their energy systems and also some kind of protection from extreme conditions, but not to the same level as humans. Humans are more delicate, you could say. So, and in terms of energy, the energy problem is still there for everybody, but at least robotic craft is lighter, can be made to be more nimble and lighter, so their energy needs will be less than having to carry a crew and the whole life support system and the whole possibility of what? Shielding from cosmic radiation. So those are some of the problems. So you now found out that the direction shifted towards more of space, robotic space missions to all the different planets. Most of the countries were now launching robotic space missions, and very few were talking or were investing in manned space missions after the Apollo mission. And don't forget that the Apollo mission, there were drivers for the Apollo mission in terms of the space race. There was a competition about who will come out on top for the space race between the Soviet Union and the United States. So there was an extra motivation for a manned mission, because that's like hitting the punch. So, but after that, the enthusiasm subsided a little, but the attention shifted more towards robotic missions, to including the moon too, and all the other planets. So in terms of now the future, so in terms of yes, in terms of future directions, we also expect, apart from the attempts to now make more inroads towards manned mission, SpaceX, Elon Musk's SpaceX, has been at the forefront of efforts to put together a manned mission to Mars, but it's still in the planning stage, because planning and preparatory stage, because of some of these constraints I've told you: distance, speed of light, refueling, restocking, okay, human life support, cosmic rays. So that is why those things are still being worked out. So, but a lot more countries and international collaborations are putting out robotic space missions, and a lot is being learned, has been learned about many of the objects in the solar system. So what we expect now is that the push through robotic space missions will continue, and it will even get more advanced because of the need for autonomy by those robotic craft, because we're moving farther away now. So, and what will help in that autonomy will be an integration of artificial intelligence and autonomous systems into the robotic crafts could allow them to operate on their own more. Then when they gather information at the appropriate time, they send their telemetry back, either as a signal radiation, or they send back something, a probe, carrying the data. So we expect that those deep space missions to the outer planets and other parts of the solar system will continue, while efforts to work on the problems and constraints that affect manned missions will also continue. Because of course, you know that there is no replacement for a direct experience, because the human being is there and having direct experience is different from the telemetred data. The two cannot be the same, because somebody who is there can describe how he felt when he was there, which is not the case with telemetry. You're just analyzing data, images, videos, and all that, but it's not a direct experience. While you're there, you could take new decisions. That's not the same with robotic mission. Only the programmatic possibilities of the AI robots is what is possible, not independent new decisions. Okay. So that is what we have in terms of the possible new directions in robotic space missions in the outer parts of the solar system, also in the inner solar system, because you also have the inner planets and the suns. Remember, they are also sending spacecraft near the sun, not into the sun, of course. No spacecraft can be sent into the sun because the sun will basically vaporize that spacecraft, but near enough to be able to make some studies that will complement the ones we're making from a distance. Well, the other one is now, how about further than that? Interstellar, beyond the solar system. You know, when we were started, I talked about baby steps, that even with these 60 years, it's still like we're just starting. Yes, because the universe is so big. So, but no problem, that's baby steps. Since we're already talking about Voyager 1 crossing the heliopause, so we are at the fringe of our own solar system. Then people are speculating, proposing about possibilities for interstellar travel, interstellar color. But for now, all those are still on the speculative domain. That is, people bring out ideas of what could be possible, what we should do to further extend space exploration to the stars and other exoplanets. So if we're already having some limitations here, both for manned missions and for robotic crafts, you can now imagine that will be multiplied many times for interstellar missions or travel. But no problem. What is complementing that is those constraints is what is coming from astronomy. I already told us at the beginning that there's a complementary role between astronomy and space exploration. So astronomy has also expanded in terms of the thrust to the outer extrasolar other stars, and we now have discovery of so many extrasolar planets through very fine techniques in astronomy. So through discovering techniques and methods of discovering the various planets in other stars and then mapping those planets and their characteristics. So these efforts, in fact, we can say there's an explosion of discoveries through astronomy about extrasolar planets. So these discoveries are now complementing the limitations we have about current limitations we have about interstellar travel. Okay, and giving us at least something to chew. Well, maybe with time, who knows what could happen about the possibilities of interstellar travel. Some people are even talking about faster than light travel later. Of course, we know that current physics doesn't permit that, but nobody can say about what could happen in the future. So that is it about possible directions that space exploration could take and how it is being complemented by astronomy. Those fine techniques are discovering extrasolar planets and telling us about it. And then what we're learning in the solar system is now being used as a reference or basis to be able to now relate those discoveries about extrasolar planets. Since we now know more detail about our own, then we can project that detailed information into other systems that we don't have adequate detailed information.
Yes. Sir Frank, I think you can summarize this part so that some students can interact with you. Some of them are already dropping questions on the chat, and some may want to give questions directly to you so that you respond to them before we go on break.
Thank you very much. Yes, so that is these are the directions that I perceive that things are going. Moving of more robotic crafts and using AI and autonomous robotics to make them better, perform better. Then also exploring the more possibilities for manned missions. Then in terms of interstellar, the research and the speculations on interstellar are still there, but astronomy is now also giving a feedback about exoplanets, many different worlds. Then you see the relationship is dual. Astronomy gives back to space exploration. Space exploration gives back to astronomy. Remember that many of the spacecraft that are discovering those extrasolar planets like Kepler, James Webb, are space exploration craft. That is, there is the same technology or used in space exploration that are used to launch, control, deploy, and receive information from space telescopes. So the two are always working. And, I expect that that will continue. The reason is because the more the distance, the more the limitations. The more the distance in astronomy, the more the distance, the more the limitations of an Earth observer. So you now find that it is in that area where there's more limitation to space exploration. Astronomy can complement space exploration the most. We're now talking about extrasolar planets, the study of galaxies. So is it what we learn about the solar system, we'll project it to other, the extrasolar systems in other stars. What we learn about the Milky Way galaxy, we tend to project it to other galactic systems, external galaxies that we can study in the same close way we can study the Milky Way galaxy. So that is the trend. Yeah. So I think I can pause here for interactive feedback.
Okay, thank you so much, Sir Frank. We have listened to you, and I'm sure that our participants have also listened to you. This time around, we take about 10 to 15 minutes for interactions, comments, questions, and further clarifications. But before I look at the questions that are there, sorry, I think I observed some mix-up in your slides while you were presenting. Maybe after this presentation, you get across to us the complete slides so that it can be uploaded for the students for subsequent use. I think that is the trend, and I hope you will do that as soon as possible. So once again, I thank you for making out time to give us this lecture. And yeah, this is a time for interaction. So if you have any comments, questions, or maybe further clarifications from your end, you can raise your hand and then we will recognize you to speak. Meanwhile, I have some charts. Okay, yeah, somebody said the slides were not there, which of course, this is what I have also observed as well. there was a mix-up. I think it was moving from one end to maybe a different thing. So, but that is not a big problem. You have to make the slides available so that we can upload it to the students. Then, I think so. Yeah, which types of robotics used for interstellar and space exploration? I think you can get the question.
Yes, I can get it.
It's talking about the robotics, which type of robotics are used for the interstellar and the space exploration. So you can give further information on that. Then why are the, okay, it's also talking about the slides.
Right, yeah. Okay, yes, Aman, yeah, thank you for your question. Sorry about the mix-up with the slides. It's a logistic problem on this. We'll work on it. But at least I can interact with you, orally right now. Yes, you asked the question about robotics used for interstellar and space exploration. Basically, for interstellar, we're not yet at the level of true interstellar when it comes to space robotics. I think while I was talking, I mentioned basically that where we are at the fringe, the closest that comes to what could be called interstellar, which is not really yet interstellar, is Voyager 1 and Voyager 2, which are trying to, they said it has crossed the heliopause and is now moving to the outermost fringes of the solar system and from there beyond. So basically the robotics, when we use the word space robotics, we're not really talking about a new kind of robotics. It's all basically the normal robotics. Computer-controlled autonomous systems. That's what robotics is. That is engineering systems that can achieve one purpose or the other that are more or less autonomous on their own. They move on their own, they work on their own after being programmed. There's software that controls the hardware, okay? So that's a robot. We have industrial robots that help us to manufacture things. We also have space robots that help us to assemble things in space, robotic arms. So it's the same concept of robots. Basically, a robot is made up of sensors, actuators, and then control. That is integration. That is, you have systems to be able to sense information from the thing you are controlling or manipulating. Then you have other systems to be like cameras, for instance, pressure sensors. So it's almost like simulating the human body, touch, vision. So you're sensing information from the environment. Then you're now trying to manipulate the environment. Those are the actuators. You try to do things, you move things, you shine light on things, you make sound. These are the actuators. Information moving away from the system to the environment. Then how do you marry these two together? Because that's what control is all about. So there's a computer or a software that now decides, okay, if you get this type of information from outside, this is what you're going to do. That's what robotics is all about. So it's this same general concept of engineering robotics that are now being applied in solving a space mission. What do we want of a space mission that we say, like Pathfinder or another rover, Sojourner that we send to Mars? We want something like a vehicle. After it has been launched to space, then something will leave the spacecraft, maybe a lander, that will now descend in Mars, land, and then maybe move around in Mars, take pictures, do some experiments on the soils, get data, record it, and now later send it back to us. So that it's as if we did it, we are the ones that are. So if that is the case, then we are now going to design it with that in mind. That's why we call this space robot. It's going to design the nature of man, the kind of environment it will meet, or otherwise it will fail in it. The same thing you would do if you wanted a robot to go and explore.
If you are still talking, we can't hear you.
Oh, okay. Yeah. Can you hear me now?
But very faintly.
Wow. Okay. Yeah.
Yeah, it's
So
better. It's
it's
better
better
now.
now. Okay.
Yes.
Okay. So it's basically the same concept of engineering robotics, but now applied to achieve a space mission, a specific space mission. The example I gave is if we're launching a Pathfinder or Sojourner as a lander to go to Mars, land there, and then rove around, take pictures, make some measurements, maybe about the soil, maybe about the atmosphere. If we have these as our mission goals, we now have to design the whole robotic system, all the sensory systems, all the actuating systems, all the integration and software computer systems that will integrate the two. And all the data storage and telemetry system will also be designed with that in mind. Because that's the only way that that mission can be, achieved. So why we call it a space robot is just that it's now designed to achieve a particular space mission. So you now find out that, okay, to go there, do all those things, capture the data, and then telemetry it back to us. So what we're trying to say where AI will come in is, basically AI is about now adding much more layers of intelligence into the system. We now have a challenge where we now want to make those robots to take more decisions by themselves without connection to this. That's where the AI comes in. It has to have a model of its environment and take decisions. I mean, of course, decisions are programmatic decisions in terms of AI, of what it wants to do without support, direct support from base station. We're now making it more generic, what it can do. Beyond what maybe if you have a factory robot, the environment of the factory robot is very, very well constrained, limited. But now you are in an open environment, so you're almost like behaving like a human being. You have to be set by so many different variables. So what kind of decisions would you take there by yourself without direct human support? Yes, that's. So I hope that kind of tries to throw light on your question. Aman.
Yes. Oh, yes. I'm here.
Yeah. I hope you
I said
listen to this explanation.
yes. I was listening to that the robotics is like uses like the imitation of like the human being for sensing, and that you can
Yeah.
use AI to simulate different space explorations. And I heard about the
That is,
part about the technical difficulties, and that the slides will be available.
Yeah.
The
yeah.
the the one thing that I wanted to say is, what would be the difference between the two, between AI and robotics? And my last question before the break would be, if we create a successful biosphere and we use renewable energy, would that like boost if effectively space exploration so effectively that we'd be able to travel beyond the solar system and to be like a type 3 civilization on the Kardashev scale?
Okay, thank you for that. Yes, you talked about renewable energy and the self-sustaining biosphere based on renewable energy. Yeah. Yeah. My take on that is the Earth, which is our biosphere 0 or biosphere 1, our model already is a self-sustaining biosphere that is powered by renewable energy, and that is the solar energy. Yes, the plants, all the plants and animals are driven by solar energy, and it's renewable and sustainable. So we already like have a model. Now the challenge here when we try to project that to an autonomous self-contained space system, whether human life support system, that's a human life support system that is sustainable on its own, apart from the Earth, not being resupplied by the Earth, is that if you remember something about solar radiation, you know that the solar radiation does an inverse Queller decrease as you're moving away from the sun. So the insolation on Earth is the solar constant, about 1.37 kilowatts per meter squared. So moving towards Mars, towards the outer part of the solar system, the level of solar energy just, appropriately decreases. So there's a limitation there because you're trying to depend on this same solar energy to be able to power the self-contained regenerative system. And now the source of that energy is already decreasing. So that's a major. Apart from the very fact that solar radiation in itself is not a very energy dense form of energy. It takes a lot of costs and material to be able to gather it. Because you're now going to talk about huge arrays of solar panels in space or attached to that system. And that makes the system already very massive. So these are some of the limitations of the use of solar energy. So maybe something else can drive or power that self-contained system. And people are already exploring fusion. Of course, fusion research is ongoing. It hasn't become practical. So that's why we say energy is currently a what? A limitation. But the research is on, is work in progress. So that's the stuff about an artificial biosphere. Of course, an artificial biosphere must have a potent energy source to power it, whether it is the sun or whether it is a fusion energy source, but it must be there because the whole thing, the whole ecosystem, the whole biosphere runs on energy. There's an energy dissipation, energy comes in and gets used and dissipated as heat. So the same thing will happen to an artificial self-contained biosphere, human life support in space. Whether it is in the planet as a space colony, or whether it is a spacecraft in space or a space station in orbit, is the same. The current space stations right now, like the ISS station or the Mir, the Russian one that was there, or other ones, they are not really self-contained. They are not self-sustaining in terms of the human life support. They are dependent on resupply of all the human requirements from the Earth. Regular rocket trips are always needed to supply them. Both, yes, there's some attempt at recycling some of the water, some of the air, but it hasn't achieved the full value. So you now find out that there's, and then if you now have to go further to Mars, to the outer part of the solar system, then there are serious logistic challenges with dependency on resupply and restocking, regular restocking and resupply from the Earth. So that is that part. There was a second question he asked. Yes.
The part of that
Yes,
other part was, are
AI,
you familiar with the Kardashev scale?
Yes, I am. I
Yeah,
am familiar with that. Let me talk about that.
yes.
Yes.
So if
Yes.
we were able to have a regenerating biosphere and sustainable energy, would we be a type 2 civilization on the Kardashev scale?
Okay. Well, the Kardashev scale is denominated in terms of the ability to use the energy, solar energy on a planet, for instance, capture it all and use it by a civilization. And the next stage is using the whole energy from your star, the sun. And the next page is talking about, type 3 is talking about the whole galaxy's energy. Now, what we're talking about here is not actually on that level. You could talk about it in terms of like 1.5 or something, in the sense that you're not trying to capture the whole energy of either a planet or a solar system or a galaxy. You're just trying to have your own self-contained system for exploration within your solar system, and you want an energy source for it, and you want a system to be able to regenerate the life support for the humans within that, the human crew within that. So I wouldn't put it exactly within the Kardashev scale, because it's not really, it's just trying to solve a different problem. And the Kardashev scale itself is like a projection. It's not really like it's something already real. It's like a projection about possibilities. Possibilities if human beings, our use of energy keeps advancing and then we're able to capture the whole energy of the solar energy in a planet. Then the next level, capturing the whole solar energy. These are projections, which means that speculative. They are more on the speculative level about the possibilities of the future. So we're dealing with what are our possibilities as from now on. Yeah. So AI, AI
Oh,
and
yes.
robotics are related in the sense that your regular robotics, you're just trying to enhance it with AI, the capabilities of AI as the AI is developing. More intelligence, more autonomy.
Okay, with the part about the AI, the last thing what I wanted to ask is what is the difference between AI software and robotics? Because especially with the software part, people tend to mix it up. So could you distinguish the three, AI,
Okay.
software, and
And
robotics, please?
robotics. Okay, fine.
Yes. The difference between the three. Okay.
Yes. Think of the robot as a hardware system. That is, there's a hardware system that does something in the real world. That's what a robot is. But it has a software powering it. That software is computer software, computer programs, algorithms. AI just is another system that moves algorithms or computer software to a more advanced level. So we can deploy AI software to control robots. Then it will not be an ordinary robot, but AI enhanced robots. Let's put it that. Most of the AI people talk about, ChatGPT and all that, are being deployed online. That is just a software you're interacting with through the internet or through your computer. We're not yet, most people are not familiar with AI that can be used to power systems that are, robotic systems that are not, software connected to systems. But that is also possible because there's no restriction that AI will be ChatGPT and all. No, it's about being able to use the advances in artificial intelligence to do the same thing that algorithms and software have always been doing before, but now in a more advanced form. I hope my attempt to answer your question makes some sense.
That's what I get from it is AI is like you could say a hybrid of the software. Like the software is the parent and the AI is the child. So it's like a more evolved version, and then
Yes, a more,
robotics is
yes.
hardware.
Yes,
Thank you.
robotics, there must be hardware in robotics, but you could also use AI to enhance it.
Professor, could you please make your contact available? And
Okay,
thank you for the presentation and answering the questions.
okay. Thank you very much, Aman Harun.
Yeah, thank you
Because
so
it will
much,
help with
Samuel.
my technology and space exploration
Sure.
research
Good.
that I'm also doing. Thank you,
You're welcome.
professors.
Yeah,
Thank you.
Thank you.
thank you so much. Thank you, participants. I think we have come a long way this morning, and we have to go on break. Christian, are you there?
Yes.
Okay. So I think we can go on break now and reconvene by 12:45.
Okay.
12:45 for the second segment. And once again, I thank you for the patience and for active participation. Yeah, I will. We will post his email contact so that whoever that wants to interact with him further can as well do through the email. We will do that, and it will be available for all of us. So thank you so much, and see you by 12:45 for the second segment. Bye.
Bye. Prof. Finba,
Yes.
can you call me on phone? Maybe on WhatsApp. Yeah.
Okay. Okay. Good. Yeah, we are welcome back to the second segment of today's lecture on space exploration and robotics. And this second segment, the discussion will be led by one of us, a very popular one on the platform, Christian Ikechukwu Eze. Christian Ikechukwu Eze is a doctoral fellow at Nicholas Copernicus Astronomical Center, Warsaw, Poland, and also affiliated to the Department of Physics and Astronomy, University of Nigeria. Christian is working on a wide range of fields, including space robotics. And I think he is going to talk to us this afternoon on this aspect of the course, Introduction to Space Robotics. So Christian, it's over to you. You will interact with us for about 1 hour, and then we ask some questions, and then make some clarifications. Thank you.
Okay. Thank you, Prof. Fimber, for the introduction. And welcome once again to the program. The previous presenter, my colleague Frank, discussed in detail the introductory part of this course, space exploration and robotics. And I may most likely start by reviewing some parts. Okay, can you see my screen?
Yes.
Yes, you can see it.
Okay. How do I move? Okay, yeah. Okay, during the first segment of today's lecture, you've already heard about a series of limitations to human exploration of space, and that these limitations, to overcome them, we have to resort to independent autonomous systems in space, which are robotics. And like Frank said, these are computer-based autonomous systems, which have both hardwares and so many other components, as well as softwares. And here I'll just give a summary of why do we talk about robotics in space. One is because of human access, limited access to space, which Frank already talked about. Then the second one is long mission duration. For instance, if you launch a satellite or a rover or whatever, it remains there for quite a long period of time. And within this period of time, it keeps observing, keeps sending data. You have an avalanche of data coming from these systems that at some point, if you don't plan well, you run into problems storing those data as well. That, of course, is why we have ground-based data stations. Then the third one is the dangerous and remote environment we have in space. Of course, humans can't just go there. A lot of challenges abound, starting from either zero or microgravity to the surface hazards we have. For instance, if you are talking about Mars, even if you're able to go to Mars and survive, there are some challenges on the surface, assuming you have other things available for you to survive there. So some of these dangerous environments, the radiations and other things actually pose serious challenges. And because of that, humans don't go to space, and we have to rely on robotics. Then the next one is precision and repeatability. Because these are controlled systems that already take precise measurements, they give us clear measurements. Let's use, for instance, maybe a space satellite, for instance. I work with the TESS mission, that's TESS data precisely, and TESS is the Transit Exoplanet Survey Satellites, which studies stars and planets and their host stars. So, and if you use these space missions to observe a star and use ground-based observatory to observe a star, the quality of data you get are entirely different, because those ones in space don't suffer from atmospheric extension and other problem on the atmosphere. So they are already beyond this atmosphere, and they give us very precise and good quality data. Then what are since scientists have resorted to sending robots to space, then what are the applications? I just listed a few of the applications, and here we have planetary exploration. When we talk about planetary exploration, we talk about the exploration of Mars and other planets. For instance, we have some Mars rovers. So when we talk about rovers, we talk about those things that land on the planet and still drive on the surface, for instance. Maybe the Viking 1, the Mars 3, the Perseverance, all these are Mars rovers. Incidentally, the Viking 1 was actually the first one that landed successfully and drove successfully on Mars for some time. It was launched by NASA, and prior to that, Mars 3 was already launched, I think in 1971. But it just drove for a while, a few minutes and then a few seconds, and it had a problem. So it wasn't regarded as a very successful mission. So the next thing is an on-beat servicing. If you have maybe a space station, for instance, you know the astronauts go to space station, you have some robotic manipulators that you have in this space station, and you can use some of these robotic arms to service some satellites in orbit. Although it's still very challenging, and for people to do it, you have to plan well ahead of time, that you may be having an accompanying robot system that can service such satellite or such autonomous system in space. Then, Then we have the space station, the operation of space station. I've just briefly talked about it. And we have the asteroid sampling and redirection. So what do we mean by asteroid sampling? Maybe taking samples from asteroid or redirecting the as flying asteroids. You can do it with robotics in space, because you can use maybe a robotic arm in a space robot to maybe either drill through an asteroid to take a sample, or you create an impact in an asteroid to take a sample, or if you want to redirect an asteroid, you can use a space robot to drill in that asteroid, and while the mass is being ejected from the asteroid, the recoil force can impact the asteroid and change the direction of the asteroid. So if there are serious asteroids that are posing serious danger, such things can actually be resampled or redirected. Then we have different types of space robots. And here we talk about rovers. I've told you about rovers. I'll give an example like the ones that go to a planet or go to anything in space and land on the surface and try to explore the surface. So those are rovers. And predominantly we have had history of rovers in Mars, I think probably in Moon, if I remember correctly. And then we have robotic manipulators. These are robotic arms attached to some space satellite or space telescopes or space robots. And then we have free-flying robots. Maybe some satellites could be attributed to free-flying robots. There may be examples of free-flying robots, because once you launch them into orbit, they become a bit semi-autonomous, and they just beat around the Earth in the orbit you launch them into. They can be launched into depending on what the science, into Lagrangian 1 orbit or the Lagrangian 2. Then we have the core components of space robots. The first one is the mechanical structure. Like what Aman asked a question earlier about the difference between space robots and softwares. And these core components will actually give you the clear picture of what you can see as the difference. So you have the mechanical structure in a robot. In this case, you have the joint, you have the mechanical wheels, the actuators, and all that. And then you have the sensors. You have the onboard computers. These onboard computers actually have softwares. Uh, Currently, you can use AI to write such softwares and do whatever thing you want to do. But I don't think if they've started using AI, generative AI completely to power space robots or to plan and launch space robots. Then you also have the power system, which you have the solar power panel, the battery, and so many other things. And you should bear in mind that most of the times when they build a space robot or a telescope, for instance, here on Earth, before launch, the thing is folded. I will demonstrate as we progress with some examples. The thing is folded in such a way that is attached to the rocket, which is the propeller that will launch it, is an expendable propeller that will burn off after launch. And then the robot gets detached. And then when it gets detached, some system begin to open. Maybe the panel will open, and then all these things, after opening all these things, they become functional and begin to operate. Then while designing a robot, you also have some constraints. Yeah, because you have to bear a lot of things in mind. You have to bear, because this thing is going to fly in space, you have to have in mind that you should control the mass and the volume in such a way that it wouldn't pose a problem to the mission. You should also bear in mind the power needs of this, because one is that you have onboard computers that will be using powers. Some mechanical structures may also be needing power to move. And all these things, you have to consider the power needs of this and build the system in such a way that it can get all the necessary power needs. Then you have to also check the reliability and so many other things. It takes a lot of time to build a system, build a space robot or satellite or whatever. And in most cases, we don't usually have in-mission repair. Apart from basic command control and all that, in some occasions, when it damages beyond control, then you cannot repair it. Then I've given the basic overview of space robotics, and we'll use one space satellite called Hitomi to demonstrate some of the things we've just discussed, and then I'll discuss it further. And I have to make a disclaimer that the pictures of the satellites I'm showing in this talk is just for education purposes. They are not originally mine. They are taken from the website of the Hitomi website and the Hitomi white papers. So if you look at this was a telescope, a space mission, high energy mission, that was launched in February 2016 by JAXA, that is Japanese Space Agency. And it was aimed to study the universe in the X-ray regime, X-ray and gamma rays, because it studies from energy of 2 keV to about 80 keV or thereabouts. And if you look at this, you have the solar panels here. Then you have the 4 instruments in this, which I will show later. And then these 4 instruments, you have these mirrors here. The 4 instruments are spectrometers, imagers, and gamma ray detectors. You have soft X-ray spectrometer, you have soft X-ray imager. This SXS is soft X-ray spectrometer, and this SI is soft X-ray imager. And then you have this microcalorimeter, which I will discuss later. But what it does is that it helps in getting a very high resolution spectrograph of what we are doing. So it's just is a core component of the soft X-ray spectrometer. And then you have the hard X-ray imager here and the gamma ray detector, which is also somewhere here. So this is an extendable bench here. So before launch, this thing was just folded into a very small something, which you can see later. And then after launch, it's unfolded and the length extended, and it operated for about a month and got damaged in space owing to altitude error, so which we shall discuss later. But although it got damaged in space, I decided to show it because of the unprecedented resolution of the data it gave within that short period of time that it worked. So what are the core science objectives of this particular one? The core objectives were to study the structure of the universe by considering how they evolve, how especially the bodies in extreme conditions, like black holes, how they develop, neutron stars, and all these things. And then because of these objectives, it was made to observe predominantly in X-rays and gamma rays. And within the first light of these satellites, it gave this spectra. And if you look at this, you notice that the predecessor, which is Suzaku, still launched by the same JAXA. If you check the spectra that he gave, in places where some ion lines were not even visible in Suzaku, this Hitomi was able to detect ion line at such high resolution. And this was it was possible because of the microcalorimeter. But of course, the microcalorimeter also has its own challenges, because you have to develop systems to keep it cool and remove energy from it, because it operates at about 50 millikelvin. So it has a superfluid hydrogen tank that contains about 36 to 40 liters of superfluid helium tank. So you can see the resolution here. Unfortunately, after taking some of these early light observations, the satellites had a problem, and then it got lost and could not be recovered. So this slide shows us the Hitomi design, and I'm showing this just to show you the possible designs that most of the space robots have. The first thing is you have the GPS, which of course is the communication with the Earth, and this is the GPS receiver, which is connected to this. And the GPS receiver tells you, it receives this information from this and channels the timer or the timing information to the satellite management unit, which is the SMU. So the satellite management unit also sends, this is the control unit of all the operations of the space robots or the telescope. Because it's connected to the data recorder, the telemetry communication, and other instruments here in this thing. So, and looking at this, you see we have the data recorder here, you have the altitude system, you have the four instruments that you have in Hitomi, which is the soft X-ray spectrometer, the soft X-ray imager, and soft hard X-ray imager, and soft gamma ray detector. But sometimes I think maybe I will have to clarify something. When we talk about spectrometer and imager, it just tells us about spectroscopy and photometry. For instance, if you are talking about ground-based observation, whenever you are dealing with photometry, in most cases, you are taking images, snapshots of images, and then after reducing it, you get light curves. Then in spectrograph, you take spectra of what you see and analyze it thereafter. And from this, you see other 9 boxes, which represent the components on board the spacecraft and GPS. This one, the ellipse is the satellite or the ground station. So all the components upon a space satellite or space robot that are called payloads. So these are probably the sensors and instruments and other equipment that you see on board computers and other equipment that you see on spacecraft. On satellite, you call them payloads. Then this is a slide which I decided to show just to tell you how complex the planning can be. You have the project manager, because some of these things, of course, I'm not an engineer, I am an astronomer. So I don't work on designing the space telescopes themselves. I work with already designed and launched telescopes that are already sending data, and I work with the data to do what's the astronomy that we want to do. So, but notwithstanding, we still have clear knowledge of the enormity of work that is required to ensure the success of space missions. For instance, here you have starting from the project manager, you have deputy project manager, you have other systems up to these other areas that you have people controlling it. In Hitomi, for instance, I think he had over 160 collaborators in US, Canada, Europe here, Japan, and all that. And with all the things they did, and with all the tests, he still had a problem in space after one month. That doesn't mean that that there are not some other ones that do not have problem. I remember, for instance, the test satellite was launched in, I think, it had its first flight in 2018, I guess. And from then it has been operating. Is already in its extended second extension of the mission, because most times they give, once they launch it, they give it a timeline, which is the duration of the mission. And this timeline, they put the fuel that should be able to sustain this mission for the entire duration and possibly put additional testing. So if within that period and the satellite is still functional and still have sufficient fuel, they can extend the mission and still continue to get quality data from the satellite. In some occasions, some systems might, maybe some components of the satellite might break down and you have some other components working. Let's use Bright Satellite, for instance, which is a CubeSat made up of, I think, about 6 CubeSats. And at some point, some of the satellites stopped working. Some were working and some stopped. And the few that were working were still sending sufficient data needed for science. Okay, and then this is a summary of the organizational chart on how to, this requires planning, it requires control, and it requires planning before the development, that is the initiation of the plan. Then it requires a lot of simulations during the planning to simulate its operation and the workability of the components. So most times these components are built separately and then assembled together. And after assembling them together, they can then be launched. And you understand that when you are launching this, a satellite is usually attached to a rocket. And by the time the rocket starts burning fuel, the thrust from that fuel propels the rocket further. And the rocket keeps burning itself. So the rocket sacrifices itself as it launches the satellite to space. And getting towards the particular orbit where the satellite may be detached, it might be given a kind of tangential velocity that will align it to the orbit. And the satellite, once it's already in the orbit, it unfolds and starts working. But before this launch, all the necessary simulations are already conducted on Earth to see the type of data that you get from this satellite, to see how this satellite will move in that space, to see even the launch operations of this satellite. You can visualize all these simulations and detect possible errors and then try to correct them and control some of the things that are within your control. Okay, then I will go into the discussion of the individual components of Hitomi. For instance, here we have the 4 components. You have the soft X-ray spectrometer. I'm showing predominantly, this view is predominantly the sensors. And we have the gamma ray detector. We have the soft X-ray imager, and we have the hard X-ray imager. So, of course, I still put this thing here again and pointed arrows to where they are. So you have this here, you have this other one here with this mirrors and the spectrograph. So then we have the key parameters of the payload. I've already told you what we mean by payload. And here you have a summary of the energy range, the focal length of the mirror in each of these. And then you have the effective area that this thing covers. You have the resolution and so many other things. I don't have to read it one by one, but these are the key resolutions and the temperature they operate in. So, and if you look at this, they are all operating at very low temperature. So while you are also trying to maintain the temperature as low as possible by creating heat sinks and all that, then you are also trying to ensure that maybe tubes or pipes connecting to those equipments don't freeze. I remember I was in an observatory late last year, and we were trying to cool the infrared spectrograph. We used liquid hydrogen, and then there was a little problem with the hose, and then we just had to improvise another hose while waiting for people that will bring the main one. And because of the temperature of the liquid hydrogen, the hose that we used after the first use, it froze, and then it started cracking along the line. So you have a lot of challenges when you're observing at these extreme low temperatures, because you have to first of all ensure that the temperatures are kept as low as possible. And then you have to ensure that the components around those low temperatures do not freeze. So starting with the soft X-ray spectrometer, we have the 2 components, which is the X-ray telescope, in most cases the mirror, and takes images. And then we have the X-ray calorimeter. And this X-ray calorimeter is a 6x6 array. So what it does is a specialized instrument that measures a slight increase in the temperature. So because it works at 50 millikelvin, so whenever there is a slight increase in temperature, it will detect it. And what causes the slight increase in temperature? Whenever the system detects an X-ray photon, it raises the temperature slightly. And then this rise in temperature is detected in that system. And it gives you a very unprecedented resolution that just the like of the one I showed earlier. And here is a full setup. Most of these are engineering distance, so I don't have to describe each component one by one. Like I told you earlier, I'm not an engineer, I'm a scientist. So, and the second one, this is, this is the X-ray, the soft X-ray dewar. Oh, that's where the cryostat or the liquid helium is, and it helps in sustaining this system at such low temperature, and then ensuring that it does what it's supposed to do. Let me give maybe about a few minutes for questions before we continue. Does anyone have any question? Because I have this screen on, because I'm sharing screen, I don't see the charts and all that. So if there is any question, you can let me know. Okay, I will assume that there is no question.
No questions, sir.
Okay. Then this is the next one, which is of course, we've told you that the X-ray spectrometer uses X-ray telescope and all that. And because it is dealing with X-rays, which can penetrate a lot of materials, it employs what we call the Volta 1 telescope. I think Volta, because I don't think if it's an English name. And somewhere here in Poland, for instance, this W is pronounced as V. So, and then this Volta 1 telescope is designed in such a way that you have a grazing incidence instead of a direct hit on the system. Because if you have a direct hit, if the X-ray hits it perpendicularly, what happens is that the X-ray may eventually be absorbed because of its energy, or either it gets absorbed or it gets transmitted through the system, depending on the system you are using. So the best approach is to ensure that you have a telescope design that will graze through this and either gets reflected or gets refracted into another system. Okay, predominantly gets reflected, not refracted. Yeah. When it grazes, it just it doesn't pass through that. It returns to another setup. And this is part of the cryostats that helps to cool that system. Okay, this is a cross section of the soft X-ray spectrometer. I won't be discussing this in detail, but see the point where the X-ray is going in, and then I'll be talking about this inner section in the next slide, where you have the tank and some other things that will reflect light here and there and sustain the temperature that you expect to have. Okay, and this is a closer view or cross section at some points where you have this DEWA here, you have this shield, and what happens, you also have this, which is a kind of reflector that when heat gets to this, it gets reflected into space. Then you have also this outer surface of DEWA, and this is coated also. The coat also helps in reflecting some heat coming to it. So you have other areas, starting from this radiator here, and so many other components that you can see. The arrows point you to what they do, and they are all aimed at dissipating heat or creating heat sink and ensuring that what is here is kept at the optimal temperature. So we have the soft X-ray imager, which is a 6-meter focal length imaging mirror with a CCD. CCD is very common in ground-based telescope. So that of calorimeter is very rare and is usually used in high energy astrophysics, predominantly X-rays. And I think apart from Hitomi, I think the next one that is being planned to use such calorimeter is CRISM, which I think is still being designed by the Japanese. So this thing, each of the CCD is 3 centimeter wide, corresponding to these pixels, and making standard of micropixel size. If you have worked with a photometer, you notice that what the thing does is that following the pixel size, it just catches or captures an image of a particular place. And I'm talking about maybe as a photometer within the optical regime. And when it captures this image, you have, if you're observing stars, you have so many stars in those places. Of course, you may have that central star that is your target, but that central star, because it will just observe the field with so many neighboring stars, it may have some light dilution from those neighboring stars. And then for you to be able to get the actual light curve from this particular star, you may have to extract the pixels that are only covering that particular star. But you extract it in such a way that you don't reduce the pixel size too significantly, or you don't increase it too much to accommodate others. If you reduce it too significantly, then you are already reducing the quality of data you are getting. Then if you increase it too much, you're already accepting some dilutions from neighboring distance. So at each point in time, you have to study the pixels and you check the optimal size that can give you an optimal result you want. Then this one also has a mechanical cooler that operates at this temperature, minus 120 degrees Celsius. A moment, please. Okay, and here is the hard X-rays. Of course, you know, in astronomy, these soft X-rays, hard X-rays, and all that, they are just classified based on the energy ranges they cover. For instance, in the soft X-ray here, it covers the energy range of, I think, 0.2 kiloelectron volts to 12 kiloelectron volts. Okay, 0.4 thereabouts to 12 kiloelectron volts. And the hard X-ray imager covers from 5 to 8 kiloelectron volts. And that of the gamma ray cover beyond this regime. So you see this, it consists of three components: an X-ray mirror, a straight light baffle, and a thermal shield. So like Frank already pointed out, anything you are sending to space, you are considering the environment there and ensuring that you protect it from radiations, you protect it from heat, that's thermal disturbances. You also ensure that it survives the microgravity or no gravity, depending on where you are sending it. And all these things, in any instrument they are building, they are making sure that all these things are put in place. So you have different systems here. I think this is the full setup. This is the interior cross-section of it. That is assuming you bisect it and then you see the views. And okay, this one is what is supposed to be here that is zoomed into, and you see what is there. Okay, probably this may not be so necessary, but what you see here are the subsystems in these systems, where you have this hard X-ray, you have some other system that form part of it. You have these other subsystems. I won't be able to explain all. In fact, I don't even know all of them. That's the fact. Some of them are some technical engineering. Okay, and this other one, which is the last instrument, the fourth instrument, is the soft gamma ray detector. And this is a non-focusing X-ray detector with a 50 to 600 kiloelectron volts. So it detects both X-ray and gamma ray within this energy range. Remember that the hard X-ray detects from 5 to 80, and there is an overlap between 50 and 80. So it detects both X-ray and high energy distance within this range. And this is one of the advantages of space robots, because they are already in space. They don't care about the filtering by the atmosphere, because those observatories or telescopes here on Earth cannot observe gamma rays. Of course, I know we have a Cherenkov telescope that studies gamma rays, but what it does, it doesn't take gamma rays directly, because gamma rays directly don't reach it. So what happens is that when gamma rays strike the atmosphere, it creates what they call Cherenkov light that is detected by that telescope. And those in gamma rays they can analyze those Cherenkov lights, gets the map the direct trajectory back to where the source originated, where that gamma ray originated. So they do a lot of science with that. But apart from that aspect, gamma rays and X-rays don't reach the ground. They are already filtered out by the atmosphere. But if you send robots to space, like satellites and all that, you can easily detect them, just like what this one was doing before it got lost in space. Okay, this is the kind of summary of the mission characteristics, where you have all these telescopes, the instruments, and what they can do. And you have this X, I think most of even what we wrote here, I already explained some of them, like how they operate, at what temperature they operate, the efficiency or detectability, the levels of these instruments. I've explained some of them and don't have to repeat them. So, and like I said earlier, that whenever you are building satellites or building space robots, you build the components individually. Like some of these collaborations that build space satellites, what they do is that some systems, some institute will be building some components, some other university will be building another component. I remember, for instance, there's an ongoing mission that is being planned in high energy astrophysics, which is the new Athena. And my institute is part of the collaboration, and those involved are building some components of that satellite. Is expected to be launched in 2037 or thereabouts. So it's about 11 years from now. So to tell you the duration, because the planning doesn't take, it takes a lot of time, a lot of energy, a lot of resources to build this. So it takes people plan it well ahead of time, gives necessary approval, necessary quality checks, necessary validations, and all that. You don't just wake up and start building them. So here is a kind of components of Hitomi, and then when you, after building it, you see the folded section where this standard this part is already folded in here. And when it gets to space, when it got to space, it got unfolded, and you see the unfolded parts. Then this one summarizes, okay, this is a full showing the height, the exact time before launch when it is completed. And this is showing information about the mission, about the launch site, launch rockets, H2 rockets. And I've told you most times they launch this into the orbit. Most satellites are in Lagrangian 1 orbits, some are in Lagrangian 2. Like James Webb is in Lagrangian 2. Lagrange and yeah, Lagrangian 2 points. What do we call Lagrange points in satellite launch? These are possibly expected points of stability. That is where you expect that this could be very stable when you launch it into that orbit. And the Lagrange 1 point is located about, I think, 1.5 million kilometers away from the Earth and in between the Earth and the Sun. So if you have Lagrangian 2 point, Lagrange 2 points, you have it still about that's 1.5 million kilometers away from the Earth. But on the other side of the Earth, on the dark side of the Earth, when we mean dark side, we mean the side that is not facing the sun. So that is why if you check the James Webb Telescope, which is in Lagrange 2 points, orbit actually is in the cooler part of this thing and observes the dark part of the universe in the infrared and gives us a lot of information about what is happening there. The Lagrange 1 point also has its own advantages because it has a continuous source of light from the sun, and probably the solar panels and all that will be more effective and do a lot of other things. But it still has its cons because some of the radiations and the heat, if it becomes too intense, can damage sensors and other things that are on board the spacecraft. Okay, the very unique features of Hitomi. Remember, I just chose Hitomi just to give you a clear example of at least one satellites, of how they plan it and how they design some things and some of the components or the payloads. There are a lot of many other satellites, a lot of many other rovers. Like Perseverance, for instance, is a 6-wheeled rover. Remember, rovers, for instance, move on the surface of planet, unlike satellites that can just be orbiting the Earth at a particular orbit. And sometimes one wonders what happens and what keeps that satellite in that orbit without either colliding to the Earth with the Earth or flying away from the Earth. And with also with all the so many satellites you have in space, each one still maintaining its own orbit without colliding with another. So these are some of the questions you may begin to ask yourself, and maybe probably as we progress, we may answer it, or maybe during question and answer session, you can also answer it. So these are some of the unique features of Hitomi. The first one is that microcalorimeter, which increases the resolution to an unprecedented level. Unfortunately, Hitomi didn't last. So, and that technology appeared like it was somehow wasted, but they are still already developing it in another satellite that will be launched, in the future. Then you have also the cooling capabilities using those cryogenic materials, the superfluid, the cryocoolers, and so many other things connected to that DEWA and cryostats in the soft X-ray spectrograph. Then you have the cooling targets, which are these detectors and some other components, and so many others. Then I remember at the beginning when I was starting to talk about Hitomi, I told you that the mission failed after 1 month of launch. And why did it actually fail? I think it failed because of a lot of issues or some incidents with the altitude control system. And because of this altitude control, the failure in the altitude control system, then the telescopes or the satellite started spinning so fast. And because it was spinning so fast, some of the weakly attached components broke up. And when they broke up, once you start having such things, establishing balance and the equilibrium is no longer possible, because the whole thing was designed bearing in mind that the design and the motion should be able to sustain that equilibrium. So, but when it broke up, then it developed other problems, and then the Japanese agency reported 3 altitude anomaly problems, and these problems were summarized in one of the reports, which I just showed briefly here. I don't have to read it. These slides will be available on the platform, so you can see this. So, but what we're trying to say here is that at the telescope, irrespective of the fact that it had some of the most advanced technology that would give one a very precise measurements and other things, then it still failed after some time. So tell you the challenges involved in exploring space, either using manned robots or unmanned robots. When Frank was talking, he talked about most of the challenges involved in using manned robots. But even in unmanned ones, like ordinary satellites, for instance, you still encounter a lot of challenges because of the challenges in space. And any slight thing, if you can't immediately control it, then it may degenerate to something serious. So you still have control systems and data centers here on Earth, where you can use soft ways to, if you notice any problem, you can use soft ways to either communicate with the software or the onboard computers, and then they try to execute some motion or mission, depending on whether it has those maneuvers or whatever, arms, robotic arms that can do some other things. Then, we've been talking about, initially we talked about the introductory part, the components, why we use robotics. Then we gave example of a particular telescope, and we talked about the components of these telescopes, the launch and other characteristics. And then we have to tell you again that once the telescope is, or the robot is launched to space, you have to consider a lot of other factors, such as the robot dynamics, the optimal estimation of the robot status, that is the position. You have to consider the position, you have to consider the velocity, you have to consider the orientation. Then you also have the control, and all these things play key roles in the success of the mission. In dynamics, I don't have to come here and start giving you the rigorous physical relations governing all this. So, but you should bear in mind that since this is a satellite in space orbiting around the Earth, then you have is in motion, and a lot of things are involved. At least the first basic one you should bear in mind is your Newton's motion. If you get further into advanced this thing, you have Newton's Euler Lagrangian equations and all that, which I wouldn't talk about here. So but in summary, we're trying to let you know that what you have is a kind of coupled dynamics. You don't have a flat base. You don't have a fixed base. It's not like here on Earth where your cars are driving on the surface of the Earth. There, you are just in orbit, and then you are orbiting the Earth, and the Earth is also moving, and both the Earth and the Sun are also moving around a particular center. So you have what we call coupled dynamics. All these things are moving together and moving at certain speed. Then it depends on where you launched the satellite, because if you are just using communication satellite where you put at a particular stationary geosynchronous orbit, it will be, the motion will be in such a way that is synchronous with the motion of the Earth. And because of that, you are just observing a particular position of the Earth in most cases. So we have talked about this estimation. So using the information or the data you get from these systems, the maintenance data and other things, you can reevaluate the position, the velocity, the orientation, and all that. And if there is any problem, you can send some commands and other software commands that can help control some that are within controllable limits. Then you also have the control approaches, which I've listed here. And then you have the space environmental overview here. I think Frank also covered it to some extent. In space, you have microgravity, and some places you may have even no gravity. So depending on where you are sending the space robots, there may be no restoring force at some point because you have no gravity. So what it means is that you'll be controlling the spacecraft with the robotic arms. And by the way you control the robotic arms, the whole spacecraft may be moving in line with how the robotic arm is moving. is more of uh, seeing, if you are to visualize it here on Earth, you may liken it to what you see in some science fiction movies. But actually, we're not talking about fiction here. We're talking about real things that's actually happen. So you also have vacuum in space. And if you have vacuum, what it implies is that there is no convection cooling. You know, here on Earth, um, you don't have vacuum, which means you can have convection, air circulating from a cooler to hotter region, then from hotter region it moves back, it moves again, and you have a cyclic cooling pattern, a convection cooling pattern. But there is no such thing, which means if you are planning to send something there, you must have to design it in such a way that you have all the things to cool whatever gadgets that you need to cool down there, because you don't expect it to. And then you have the radiation problem, and that damages some electronics and sensors and all that. You also have extreme temperature swings. Like if you have this thing where some part is facing the sun and some part is facing a cooler region, that other part is very probably very hot, and the other part is very cool. And um, if the telescope is not designed to withstand such extreme distance, you may run into problem. Then you also have dust and regolith. Apart from interstellar dust for those flying objects, you can have dust on the space of the planets, like when you are talking about rovers on Mars, for instance. You can have tiny particles and other things on the surface of Mars. So what are the key takeaways here? We have this space robotics is multidisciplinary. It doesn't just involve one particular discipline. So you have engineers, you have astronomers, you have physicists, you have a lot of, is a very broad multidisciplinary area that can bring in a lot of people. For instance, if you discuss the European Space Agency that builds some of these European space satellite and all that, or the NASA in the US, you see that they have a lot of people, either astronauts, engineers, astronomers, physicists, and a lot of people that contributes to the success of the mission. Then the next one is the environment strongly shapes design. Depending on where you are sending it to, you have to bear in mind the type of environment you are sending into, and you have to design it in line with that environment to be able to survive the environment. And then the next thing is the dynamics, the estimation, and the control are central. So after launch, the key things is the motion of this thing. And for you to understand the motion, you have to estimate a lot of other parameters, which I've pointed out here, like the position of this, the velocity at which it's moving, the orientation of that telescope at each point in time. All these, there are telemetry data that you get from the telescope, and you get all this necessary information and take all the necessary steps to keep it going. Then you have the robots enabled future, that robots enable future exploration. Yeah, I think the future prospect is actually great because we are in an era of generative AI, and it's possible that in the future, instead of all this analysis that humans are doing, getting telemetry data to analyze what is happening there, then you can just use generative AI to plan all these things, and then the system will be studying the environment by itself, reanalyzing the data automatically by itself, and giving you all the necessary information, and changing the directions or doing whatever thing that is necessary at each point in time. I think I will stop here. Thank you.
Good. Thank you so much, Christian, for that elaborate discussion on the subject. And I hope our participants have gained a lot from your lecture. So now we will take about 10 minutes for discussion, clarification, questions, and all that. So if you have any comment to make or questions to ask, this is the time so that further clarification can be done by the presenter. Who has a question? I hope we are still there.
Yes, we are there.
Okay. The presenter, I will ask one layman's question. When we are talking about this space exploration, I begin to wonder, where does space start? Where does it end? Is there an end to space? If there is, what lies beyond?
Okay, I think you are a professor of cosmology, and you may have even a better answer to this than me. Because in reality, if you talk about the Earth, we are just one of the planets floating in space as well. So somebody, if a layman is talking about space, he might just think is when you leave the surface, of course, the Earth atmosphere. Of course, if we want to take it strata by strata, you have to leave the exosphere, and then you know that the space above the Earth is that's beyond the exosphere upwards. So, but if you are to consider the universe, in its entirety, then you discover that this is just a planet that is also floating in space because it's rotating about the sun as well. And the sun is also rotating about a particular point in the galactic center. So I think generally we might say that generally we're all floating in space, but still standing on the surface of the Earth. But for simplicity, we might say that if we consider the Earth just as the starting point, and then consider the strata of the atmosphere, the ionosphere, and this thing, that we may consider space from the exosphere upwards. So, but I think you may give us a clearer this thing. You are also, this is more of astronomy than space applications.
I think you got it correct. We are all in space. We're already in space. Apart
Okay.
from being on Earth, there are other planets. Then, if we're exploring, you can say we are exploring beyond the planet Earth, or we're looking at other layers within the atmosphere of Earth. But basically, we are in space, considering that Earth itself is one of the known planets.
Okay. Thank you, Justice.
Yeah.
Yeah. Thank you, Justice. Any further questions or comments?
Okay, I would like to ask further. Thank you very much, Christian, for the elaborate lecture you're giving us in space exploration. If you look at the time you were describing the high energy exploration using X-rays of different types, I want to ask the kind of information you get from this exploration when you use these instruments. What does it inform you? What does it tell us? What can we say based on this information we got from these high energy instrument? This is what we can see. I mean, can we put it in a perspective that If I'm talking to someone out there, you'll be able to understand it. Let's not dwell so much on the fact that some of us have a bit knowledge of what we are talking about. We understand it, but to a secondary school kid out there, to our kids at home who may see us talking about space exploration using telescope, using X-rays, the kind of, especially high energy exploration, what kind of information, what kind of applications can we, put it to them in a layman language that this thing we say is happening out there in space. Look at its benefits, look at its application for us here in that. Thank you.
Okay. The first thing I'll have to let you know is that most of what these high energy observatories in space do is to count photons, count high energy photons. So, and of course, we all know photons as energy, as particles, as well as waves. So, and when you get these photons, you can change these photons into the light curve that describes how the properties of this particular system. For instance, if you have a flare in X-ray regime, maybe you have a supernova explosion, and because of that supernova explosion, you have an explosion of energy. So because of that explosion of energy, what you observe in that light curve is a sudden spike in the photon count at certain interval in the light curve. And you can, from that other analysis from that light curve, tell what is happening about that supernova. You can also tell what is happening around maybe the event horizon of a black hole. You can do a lot of other things by counting the photons emanating from those systems. So all these things in X-ray and high energy distinct, they are just trying to tell us about what is happening in space by counting the X-ray photons. Of course, if you are dealing with ordinary optical telescope, you are working in the optical regime, and you are just counting the fluxes coming from the stars. So there you measure the fluxes, and from the fluxes, you do other basic analysis and tell how the star is behaving. You tell the properties of the stars and a lot of other information that can follow. So I think to somebody in secondary school who may not understand some rigorous technical terms, you may just have to let him know that astronomy in most cases, or some of these telescopes, hinge on receiving either the flux or the photons from this star. They observe predominantly in the electromagnetic spectrum. So if it is observing in radio, for radio telescope on Earth, is receiving radio signals. If it is observing in the optical region, then it is receiving fluxes from the stars. If it is observing in the X-ray, UV, infrared, or whatever, okay, let me not say infrared, but maybe X-ray, UV, and all that, is getting photons from this. And you can convert these photons or these fluxes to light curve or whatever spectra and tell the properties or the behavior or what is happening in those stars, which is ordinarily are very far away and unreachable without these telescopes.
Yeah, correct.
Christian,
very
for
much.
that explanation. Perhaps I think Frank Ona has something to add to the explanation. So you can.
Okay, I think I'll stop sharing and then.
Yes.
Okay. Yeah, thank you, Christian, for that wonderful and detailed lecture. Thank you, Justice, also for raising this question. I think this is also borders on how we break down the issues about space to people who are not experts in space, that is, lay people. If somebody were to ask me such a question, generally about how do I justify our focus on studying celestial bodies, especially using high-tech, very expensive equipment to just channel on studying celestial bodies, other astronomical bodies. I'll try to approach it this way. You see, first of all, is that there's a natural curiosity we all have as human beings, all of us, to wonder about things in our outer environment. Everybody is familiar with wondering, looking up at the stars, gazing at them, wondering about them. As per that nursery rhyme, twinkle, twinkle, little star, how I wonder what you are. So that is innate in us as humans. And the whole space exploration astronomy effort is just an advancement of that process, okay? So I will generally explain to that person that we're just doing basically the same thing. And when we now, have these X-ray telescopes counting photons, then we analyze the information. What's the point of analyzing the information? To now learn and have a better understanding of the workings of those bodies that we're getting those photons from. But there's also another spin-off. That spin-off has much more to do with us down here on Earth. We already said it, the Earth is a planet having a number of motions in the galaxy and in space, motions upon motions. So we're just having as our home one particular instance of a celestial body. We're in space, moving in space. So whatever we learn about those other external bodies, we will always find uses and projections for them in increasing our understanding of our own home, our own planet. It's always worked that way. You think you're studying outside things. At the end of the day, you have what? Spin-off applications down here on Earth that affects life, that affects technology, that improves how we do things. Because space now what? It challenges you to further extremes. That is the kind of energies. For instance, we just spoke about high energies of X-rays. Those high energies we're talking about for cosmic rays and X-rays, those are not the kind we're used to on Earth. So by pushing our limits to involve extremes, we now have a better understanding that can now give us spin-off applications, even right down here on Earth. They go that way.
Yeah, thank you so much.
Okay, Prof. Finba, maybe let me just briefly address two questions
Okay.
on chat before we round up. Maybe I would not take long, just briefly.
Okay.
First, we have, starting from the last one, which subject do you need to do to space exploration? I've already said that this is multidisciplinary. You can do a lot of maybe physics, you have aeronautics and astronautics, you have astronomy, you have engineering and all that. So the closest approach, closest discipline, if you want to actually travel to space yourself, is astronautics. Incidentally, in Africa, I don't think if there are universities that are doing astronautics. So astronomy is the closest in Africa. Astronomy and physics are the closest in Africa. Then the second one is what Justus asked. To cut it short, I will tell you that NASA is not just acting scripters this thing. So what they analyze on Earth is the telemetry data that gives them information on that is the status of that satellite in space. So what they do is that they design the satellite here on Earth, plan the launch, plan the path, simulate all these things. So before the actual launch, they may have simulated the nature of the data they are going to get from that satellite, the motion of that satellite, the survival of that satellite. All these, they use physical equation, physics and all that to do it. So the data center, what the data center does is that it gets the actual data. That is, those ones they are stored there, and it also gets the telemetry data. What the telemetry data tells you is the information about that telescope, about that satellite. And that is actually what they are doing. If you have some satellites and you notice that the orientation is maybe changing slightly, but not so great, so bad, and you notice that some things are changing, you can give some command and maybe write some code depending on the possible communication between the onboard computers and what you have here on Earth. You can communicate with those onboard softwares in those onboard computers that will execute some commands to put some of those things in place. So it's a kind of just trying to do some repairs. But of course, there are no in-person repairs in those things, in those places. Then finally, I will just answer this other one, and maybe other ones remaining there. You can we can interact with any other time. Or then somebody asks, what is microgravity, and does a space robot use kinematics? Okay. Microgravity. When I was explaining it, I just used either limited gravity or no gravity. That is very minimal gravity. And when you talk about kinematics, I think basic physics tells us that you have dynamics and you have kinematics, which in most cases, if you are discussing motion without considering the force, then you are talking about kinematics. So in isolation, of course, some of these space robots will have that. And I was even, when I talked about using a space robots to resample or redirect asteroids, there are some kinetic aspect of it. But of course, they don't discuss kinematics in isolation. Instead of just discussing the motion alone, it's just better to discuss the dynamics where you involve both the motion and the compressed and the forces imparting that motion. Then as for pneumatic functions, I don't remember if they have such compressed this using those compressed A's or whatever. But of course, if they are using it, they are going to make sure that is in an enclosure where those things will not leak out. Because once it leaks out, that place is predominantly vacuum. And once it leaks out, it means that that system will fail. That system that needed to work on that pneumatic properties will fail. So predominantly they try to avoid it, but where they use it, they have to enclose it put it in an enclosure, just like they use these cooling systems in enclosures. So I think I'll stop here because we're already far beyond
Yeah, I think it's a good point for us to stop, having done so well and so long. So thank you once again, the instructors for today, Christian Neze and Frank Ona. We appreciate your time and the effort put in putting this lecture together. And we do hope that our participants, you are trying, you are doing your best, you are doing very well, and we continue to hope that you will come again each time we ask you to come. So I think we can draw the curtain here, and then we can retire and come back tomorrow by 11 a.m. West African time for another round of the lecture. So thank you so much, and bye.
Thank you. Bye.
Thank you.
Thank you, bye.
Bye.